Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Sodium-ion batteries are the hot topic in the battery space at the moment, with big claims about how they'll disrupt the battery industry. The question is, will they actually disrupt the battery industry, and if so, by when? So today, we're going to take a hard look at sodium-ion batteries, component by component, to understand at a first principles level what their strengths and weaknesses are, along with their projected cost compared to lithium-ion batteries, and how fast the sodium-ion battery industry will scale. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. The image on screen is a visual representation of a lithium-ion battery cell, which we'll use as a baseline to compare the major components of lithium and sodium-ion batteries. Starting with the cathode, the white spheres are cathode particles that are each about the size of a red blood cell. At an atomic level, lithium and sodium-ion battery cells involve a host structure made of elements like nickel, iron, oxygen, and phosphate, and the active lithium or sodium ion. There are dozens, if not hundreds, of potential ways to arrange the crystal structure of the cathode, and that in turn results in a wide range of potential cost and performance characteristics. With that said, there are generalizations that can be made about the differences between sodium and lithium-ion cathodes, which are directly or indirectly related to the larger ionic radius or size of the sodium ions. For reference, lithium ions are 0.76 or 76 picometers wide, and sodium ions are 1.02 angstroms or 102 picometers wide, or about 34% larger. Interestingly, that doesn't mean the crystal structure needs to be 34% larger to hold the same number of sodium ions. That's because the sodium ions only make up a small fraction of the crystal structure. With that said, due to the way that sodium ions form bonds within the cathode structure, most sodium-ion cathode materials end up being disproportionately large for the size of the sodium ions. Or, as Shirley Meng described it in my interview with her, the sodium ions are packed more loosely within the host cathode crystal structure. I highly recommend that video, and I'll link it in the description. As a result of the loose packing, the density of sodium-ion cathode powder is, on average, around 45% less dense than an LFP cathode material of the same gravimetric energy density. So does that mean using a sodium-ion cathode material results in a battery cell that has a volumetric energy density that's around 45% lower than an LFP battery cell? No, because the cathode only makes up about a third of the internal volume of a battery cell. That means, all factors considered, the cathode structure of a sodium-ion battery cell tends to result in a volumetric energy density that's about 15% less than lithium-ion battery cells. There are other factors that impact the volumetric energy density of sodium-ion battery cells, but I'll cover those in a moment. Despite the energy density drawbacks of the looser packing of sodium ions in the cathode, there's also a major benefit. The sodium ions can move more freely within the cathode host structure, meaning lower ionic resistance that allows for faster charge and discharge rates. Again, I'll go into more detail on that after we've looked at the rest of the cell components. As a side note, similar to LFP cathodes, the cathode of sodium-ion batteries tend to use robust 3D crystal structures that operate at relatively moderate voltages. That means they're durable to the expansion and contraction stresses that occur as sodium ions move in and out of the crystal structure, and they don't suffer from the side reactions that would happen at higher voltages. As a result, we can expect sodium-ion batteries to eventually reach cycle life specs similar to LFP batteries, around 5 to 10,000 cycles, along with high thermal stability and therefore safety. The next component to look at after the cathode is the electrolyte. After the sodium ions leave the cathode, they form what's called a solvation shell made of ions from the electrolyte solution that allows them to float through the electrolyte mixture. If you'd like to know more about that, I'll link my How a Lithium-ion Battery Actually Works video in the description. Due to the fact that sodium ions are larger than lithium ions, they have a lower charge density. That, in turn, means the bond with the solvation shells is held more loosely, making it easier for the sodium ions to shed their solvation shells when they arrive at the anode. The ease with which they can shed their solvation shells once again means lower ionic resistance, meaning faster charging speeds. Additionally, the lower charge density of the sodium ions also means the electrolyte solution for sodium-ion batteries tends to be less viscous, meaning it flows more easily, which also helps with ionic resistance and charging speeds, especially at low temperatures. The next component to cover is the anode. A typical lithium-ion battery uses a graphite anode, which is highly structured layers of graphene sheets. Sodium-ion batteries instead use a hard carbon anode that's more like a jumble of graphene sheets. So why is hard carbon used for sodium-ion batteries instead of graphite? Some people assume that sodium ions can't fit in graphite, but that's not the case. It's because hard carbon plays better with sodium-ion electrolytes, and it's cheaper and easier to manufacture than graphite because the disordered structure requires less energy and refinement. As for ionic resistance, it's highly variable depending on the structure of the specific type of hard carbon. But there are hard carbons available that offer low ionic resistance for fast charging. With regards to the energy density of hard carbon, its gravimetric energy density is similar to graphite, but because its crystal structure contains more voids, it has a volumetric energy density that's 27% lower. However, again, the anode only makes up part of the battery cell, so the impact at the cell level is around a 12% decrease in volumetric energy density, meaning a cell that's 12% larger for the same energy capacity. The next component is the current collectors. A typical lithium-ion battery uses an aluminum current collector for the cathode and a copper current collector for the anode. Even though the copper is more expensive and more difficult to source, it's required for the anode of lithium-ion batteries because if aluminum were used, it would react with the lithium at the low voltages that occur at the anode. Sodium, however, doesn't react with aluminum at those voltages, so it can be used to save cost, simplify the supply chain, and improve scalability. Aluminum does, once again, decrease the volumetric energy density of the battery cell. That's because a thicker current collector is required to compensate for the lower conductivity and strength of aluminum compared to copper. However, despite the additional thickness, the aluminum is still lighter than a copper electrode because it's a lower density material, which in turn means the aluminum current collector actually helps with gravimetric energy density. Either way, overall, by my estimate, the impact of using an aluminum current collector instead of a copper current collector would be about a 3% reduction in volumetric energy density at the cell level. Now that we've looked at the differences at a component level between lithium and sodium-ion batteries, let's look at what that means at the cell level. First, starting with energy density, the gravimetric energy density of high-end sodium-ion batteries can be similar to that of LFP lithium-ion batteries. That is, around 160 to 200 watt-hours per kilogram. However, the volumetric energy density of sodium-ion batteries is significantly worse, at around 30% less. That's due to the aforementioned 15% volumetric energy density hit from the sodium-based cathode, 12% from the hard carbon anode, and 3% from the aluminum current collector. The second difference between lithium and sodium-ion batteries is charging speed. The much lower ionic resistance of the cathode and electrolyte of sodium-ion batteries means that they're capable of peak charge rates of around 15 to 20 C, or about 5 minutes for a charge, compared to the 5 to 10C, or about 10 minutes, of leading-edge lithium-ion chemistries. Additionally, the lower viscosity of the electrolyte means they can maintain fast charging speeds at sub-zero temperatures. Third, at scale, the cost of materials for sodium will eventually go to almost zero. Let's take a look at why. The table on screen shows 8 of the key materials used in sodium and lithium-ion batteries, and some rough guesses as to the current cost of each per ton. Note that I've left finished cathode material off the list. That's because I've selected materials here that are commodities or near commodities to give an indication of the long-term cost structure of different chemistries. Although sodium-ion cathodes will use cheap materials like sodium carbonate and iron, they'll initially be expensive due to low production volumes. But over time, the cathode cost will approach the input material costs. With that context in mind, let's compare cell chemistry costs. A high-nickel lithium-ion battery cell uses mostly the top 4 expensive materials in the table: copper, nickel, lithium, and graphite, with one low-cost material, aluminum. An LFP battery uses 3 high-cost materials: copper, lithium, and graphite, and 2 low-cost materials, iron and aluminum. Sodium-ion batteries use low-cost materials for all 4 of its major inputs: hard carbon, aluminum, iron, and sodium carbonate. Why are the input materials for sodium-ion batteries so much cheaper? It's mostly due to processing costs. Let's take a quick look at each. Lithium and sodium are both relatively common in the Earth's crust, but sodium is more common and tends to form deposits in much higher concentrations. Whereas lithium might be lucky to hit a concentration of 1 to 2% in the natural environment, sodium commonly hits concentrations of around 30%, making it easier to refine. As a result, the cost of sodium carbonate is over 95% less than the cost of lithium carbonate. As a side note, most videos I've seen on sodium-ion batteries say they use table salt. That's incorrect. Table salt is sodium chloride, whereas sodium-ion batteries use sodium carbonate. Moving on to copper, it's less abundant in the Earth's crust than aluminum, but once again, its cost premium is mostly due to the fact that it tends to be present at lower concentrations, and it costs more to refine. As a result, aluminum costs about 75% less than copper. Hard carbon is slightly cheaper than graphite because, as I said earlier, the highly ordered structure of graphite requires more heat and refinement. Additionally, the raw materials for hard carbon are widely available because it can be made from almost any material that contains carbon. The same can't be said for graphite, which is usually made from natural graphite or fossil fuel byproducts. As for nickel, as is the theme, it's more expensive because it's less abundant and at lower concentrations, and because it involves an energy-intensive and often toxic refining process. What all this means is that not only are all the materials used in sodium-ion batteries cheaper, they're also more abundant and easier to refine. That matters because whereas lithium-ion batteries occasionally hit scaling bottlenecks and see huge price spikes for their input materials, that will likely never or rarely be the case with sodium-ion batteries. So with all that in mind, is the excitement around sodium-ion batteries justified? Yes and no. Let's take a look at what I'd consider is the most hyped claim about sodium-ion batteries from the last few months and use it as a springboard for further analysis. In August, there were widespread claims that CATL sodium-ion batteries hit $10 per kilowatt hour. That grabbed a lot of attention and headlines because it's S-tier level hype. I tried to drill down on a specific source for the cost claims, but all the leads turned to dust. As far as I can tell, it started with a rumor that was then amplified by a series of journalists and pundits attempting to one-up each other for clicks and clout, and AI analysis came to the same conclusion. So what's the reality? Adrian Yao et al. Published an excellent paper this year titled Critically Assessing Sodium-Ion Technology Roadmaps and Scenarios for Techno-Economic Competitiveness Against Lithium-Ion Batteries. It modeled the expected materials price floor and average price at the cell level for both lithium and sodium-ion batteries. To emphasize, that was average cell cost. So while the image shows that LFP cells should currently be around $60 per kilowatt hour, in China they can be bought for around $40 to $50 per kilowatt hour, and in places like Europe and the US, they're more like $70 to $80 per kilowatt hour. With that context in mind, Yao et al. Forecasted that sodium-ion battery cells don't have a good chance of reaching parity with LFP cells until about 2039, when they reach a price of about $44 per kilowatt hour. There is a chance that it could happen earlier in 2032, but it's less than a 5% chance. Once again, these are odds based on an average cell price. So I expect that some manufacturers in some countries, such as CATL in China, could hit that number sooner, possibly by 2030. Interestingly, the researchers forecasted that the materials prices for LFP battery materials would rise and plateau after 2030, whereas for sodium-ion, the materials prices go to nearly zero over time. That is, the researchers clearly weren't biasing the data against sodium-ion. It's simply that economies of scale are the most important factor when it comes to reducing the cost of batteries. Lithium-ion batteries have a 30-year head start, which means it'll take some time for sodium-ion to catch up, despite their lower input costs. Some might point out that sodium-ion batteries are a drop-in replacement for lithium-ion batteries, meaning they can be made on the same cell production equipment, which therefore means they should reach price parity with lithium-ion batteries in a matter of a few years. However, the analysis by Yao et al. Factored that in, and also assumed transferable learning rates from lithium to sodium-ion, and they still arrived at the forecast on screen. So, although the idea of a drop-in replacement sounds persuasive, it ignores the fact that battery cell manufacturing lines are the very tip of the iceberg when it comes to cost reductions from scaling. Most of the action is occurring further up the supply chain. For example, as I said earlier, even if the sodium and iron in the cathode are cheap, it still takes years to perfect the recipes to make that cathode material and produce it at high volumes. With all that said, it's worth noting that the Yao paper did point out an alternative scenario where there's supply shocks to the lithium-ion battery market. If that happened, it could produce a scenario where some sodium-ion batteries reach price parity with lithium-ion batteries before 2030 rather than after 2030. That is, there's still hope for the sodium-ion bulls. But that hope is mostly reliant on lithium-ion stumbling rather than sodium-ion achieving rapid cost declines. Is a lithium-ion battery materials supply shock likely? There's definitely a better than zero chance given the chatter that I've been seeing from lithium investors, which are expecting increased pressure on lithium supply in the next couple of years. So things could get interesting. What all this means is, although the $10 per kilowatt hour cost figure for sodium-ion batteries was speculation run amok and likely won't happen before 2050, it is true that with scaling and investment, the materials cost of sodium-ion batteries will go to almost zero, and they'll eventually become cheaper than lithium-ion batteries. So, does that mean that sodium-ion batteries will eventually be used for everything and fully displace lithium-ion batteries? No, sodium-ion will take an ever larger piece of an increasingly larger pie. The question is, which pieces of the pie will it take and by when? Let's take a look. Sodium-ion batteries will be excellent for grid storage because in that application, cost and cycle life are more important than volumetric energy density. So I expect sodium-ion batteries to eventually dominate that market. but not until around the mid-2030s. Why? If the best sodium-ion manufacturers are able to hit price parity with LFP by 2030, that means it's going to take a few years after that for most sodium-ion cell manufacturers to hit price parity, and then a few more years after that to scale production and for the battery grid storage market to reorient itself around sodium-ion. And to be clear, my estimate of the mid to late 2030s for sodium-ion to dominate grid storage is bullish compared to other forecasts. On screen is a forecast from Rystad Energy, compliments of the ever-helpful Lars Leesdahl, who I recommend following on X. It shows a little over 300 gigawatt-hours of demand for sodium-ion batteries in 2035. If the total global production of batteries by 2035 is over 5 terawatt-hours from all sources, not just grid storage, that means sodium-ion would only make up about 6% of global demand. I'm more optimistic, but probably only by 3 to 4 years or so, which still places sodium-ion as more of a far future day-to-day reality for products or services that most people would use. Outside of grid storage, sodium-ion batteries will also be a good choice for budget vehicles where 30% less range than an LFP battery is acceptable, or where a customer is willing to sacrifice 30% of their range for the ability to charge in 5 to 10 minutes or to fast charge in sub-zero temperatures. Yes, solid-state sodium-ion batteries could offer comparable energy density to lithium-ion batteries, but mass-produced solid-state sodium-ion batteries are at least 5 years away, and probably more like 10 years away. Even lithium solid-state batteries aren't expected to really start taking off until after 2030, and they've seen a huge amount of investment and development for the past decade. Some might also point out that due to their higher safety and lower thermal management requirements, that sodium-ion battery cells might be able to close the 30% energy density gap with LFP batteries at the pack level. However, my guess is that, at best, they might be able to close the gap by about 10 percentage points, meaning a still significant 20% energy density difference with lithium-ion. That's because LFP battery packs are already extremely space efficient. Are there any other solutions to improve the viability of sodium-ion batteries? Yes, but I don't find them convincing. For example, sodium and lithium-ion batteries could be used in the same pack to get the benefits of both. However, that would add cost and complexity. It's much more cost-effective to just pick the right chemistry that solves for 99% of the use cases, rather than mixing and matching chemistries to cover the less than 1% of edge cases. In summary, in the short to medium term, sodium-ion batteries are overhyped, but in the long term, the hype is warranted. That's because they won't affect most of our lives for at least another 5 years, and probably more like 10 years even if things go well. But from there, they'll pick up the baton from lithium-ion batteries and allow the cost of batteries to continue to decline for decades to come. The input materials for sodium-ion batteries are literally dirt cheap and highly abundant, which means the limiting factor for how cheap they can get no longer comes down to material constraints, but rather how much energy storage humanity needs. Given that humanity has infinite wants, and that means infinite energy demand, we'll eventually see sodium-ion batteries drop to near the materials cost, which is just a few dollars per kilowatt-hour. But even then, in the far future, there will still be demand for conventional lithium-ion batteries, and at far greater quantities than we produce today. That's because lithium-ion batteries are fundamentally more energy-dense than sodium-ion batteries, and we'll see ever-increasing demand in mass-sensitive applications that need that spec, like the Tesla Semi, and also aerospace applications like VTOLs. Sodium-ion batteries do have amazing fast charge capabilities and can fast charge in cold weather, But the lithium-ion batteries on the market today, even the Tesla batteries which some people consider slow charging, are good enough for most people, and will have a better combination of cost and energy density for at least the next 5 years. So, although technology disruptions can happen in some fields within a few years, it just doesn't happen in the battery industry. That's due to the risk-averse nature of energy-related industries, the economies of scale involved, and the fact that battery chemistry, engineering, and manufacturing is deceptively complex. So, disruptions instead take decades. And even then, new battery technologies don't really replace the old battery technologies, but instead add new potential applications which expand the industry as a whole. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers like my Patreon supporters generally get access to my videos a week early. On that note, a special thanks to Matthias Vrong, as well as my YouTube members, X subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.